Thank you. So I'm Cengiz Pehlevan from the Simon Center for Data Analysis, and I'm at the Neuroscience group, where we try to study how the brain actually processes data. And along that study, we came up with a few algorithms that might be helpful for big data applications, and I'll try to explain those things. Okay, so I'm sure everyone is an expert in PCA here, but if you want to, in any data analysis pipeline, one of the first things you want to do is denoise the data and project it to lower dimensional subspace, and PCA is great for that. If you look at the algorithms out there which do this online, where data is presented one at a time and processed one at a time, most of these algorithms will start from representation error framework, where what you will try to do here is the following. Suppose this matrix X is a matrix of your data points. Each column is another data point, and Y is the projected components, and the columns of W would be the coordinates. PCA in this framework be basically minimizing that cost, which says minimize the error that's made by dimensionality reduction. Of course, there's another way to look at this problem, okay, which hasn't been studied in this online context, and that's the idea of similarity matching. Suppose we define similarity of points as inner products between those points. So if that matrix X transpose X will hold all the pairwise similarities at the input. And what you want to do is you want to match the similarity at the output. You want to say your outputs have the same similarity structure. So X transpose X should be like Y transpose Y. It's excellent. So we can turn this into a cost function. And it turns out the solutions to this cost exactly does the same thing as PCA does. It projects the input to principal subspace. Okay, so what's the novelty here? So this is where we come in. We can take this cost and turn it into an algorithm to do principal subspace extraction online. Okay, and it turns out the optimization that you'll need to do to solve this online cost, okay, the operations that you will need to do will map exactly to a neural network. Its architecture, its operations, and its training will all be given by such procedure. That's excellent, and because that's good for big data analysis, because you can parallelize this as well as processing data online, so you don't have to hold all data in memory. So you might say here, okay, it's another online PCA algorithm, why should I care about that? Well, it turns out that this framework is generalizable to many other things. One of them is the following. So you can get many variants of subspace tracking. So for example, you might take your data, okay, and you might want to shrink variances in certain dimensions to emphasize variances in other directions. That's soft thresholding. Or keep the variance the same in all subspace directions. Or actually equalize them as in whitening. And it turns out you can do all these things with simple variations of the neural networks that we come up with. Maybe a little bit complicated in structure, but still can be simulated in a distributed manner and online. Moreover, our framework can be generalized to other unsupervised learning tasks, such as clustering and sparse feature extraction. And it turns out what you need to do that is basically to impose a non-negativity constraint on the output. As in PCA, you would have both signs, but here you want to have only non-negative signs. People have studied this in machine learning literature. It's called symmetric non-negative matrix factorization. What we have done is again, made it online. And it turns out this again maps to a neural network. Now, the difference is your neurons are nonlinear. And this is a particularly interesting neural network because if you take this neural network and present the data that has clusters in it, it will find those clusters in one pass. But it is also multifunctional because if you take data that doesn't have this cluster structure but has sparse features such as natural images and present it to this network in one pass, it will learn to respond to these sparse features in the data set, and which in this case would be oriented edges. So this is a multifunctional algorithm that could do interesting things. So I started by saying I'm a neuroscientist. So let me finish by commenting on that. The work that I presented was actually done to model how brain processes data. And it turns out that brain representations also care about matching similarity. So what's presented here is neural recordings from monkey and human IT cortices. IT stands here for inferior temporal cortex. It's not a monkey technician versus a human technician here. Okay, and so the message of, okay, so what's presented here is a similarity of neural responses in IT cortex to images of objects. And what you're going to see is that responses to animate objects, for example, are similar to each other, but dissimilar to inanimate objects. So there is this tendency of neural responses to also preserve neural similarity. I would say similar sensory stimuli evoke similar neural activity patterns. By the way, this was data from Craig Gescourt lab and colleagues, so this is not my data. And which motivates the use of the similarity matching framework to study brain function, and that's actually what we are doing in our group. Thank you, and these are my collaborators, Tao Hu from Texas A&M, and Mika Chiklovsky from the Simons Center.